Welcome everybody to this week's flipped videos. We're having flipped videos for both the kind of the Monday and the Wednesday sections of class this week, and we're going to come in the week before Thanksgiving and just solve some spectroscopy problems. But we're going to do a little background in this video. It'll end up being probably about 50 minutes long that you can watch over the course of a few sittings. And also notice that there's been a handout posted to the course Moodle site it's got a lot of this already pre-filled out, and you'll be able to go in and just add the important stuff. There's just no good way to talk about spectroscopy really with pen and pencil or chalkboard and chalk. So it's important to look at the pictures, and so this really helps to do it this way. So we're going to start with IR spectroscopy theory, and really it's all about a spring and masses on the end of a spring. And Hooke's law here from physics class, if you've seen it, maybe you haven't seen it yet, a little bit of math, but we're not doing any math, right? The stuff on the right is mass, and then the F there stands for the force constant or strength of the bond. So really two things impact most stretching frequencies. One is the mass of the things at the end of the spring. Hydrogen, deuterium, oxygen, chlorine all have different masses, and so you're going to observe different frequency for those things. So the mass at the end of the spring, and the other one is going to be the strength of the bond, or think of it as the strength of a spring, leading to differences in observed frequency. So let's take a look at this in practice. So the lighter the atom, the higher the frequency. That just makes sense, right? It's lighter for a given amount of energy. It's going to vibrate faster. So a carbon-hydrogen stretching frequency, we observe at about 3,000 wave numbers. But as you move from carbon-hydrogen bond to a carbon-deuterium bond, the observed stretching frequency drops in energy considerably, now only 2,200 wave number. And as you go from deuterium to oxygen, now oxygen is 16 atomic mass units, 1,100 wave numbers. And chlorine, now 35 atomic mass units, we're talking 700 wave numbers. So the mass at the end of a spring really impacts the observed stretching frequency. Similarly, here on the right, the force constant, or just the bond strength, right? We've seen a carbon-oxygen single bond at 1,100 centimeter or wave numbers, inverse centimeters. As you go from a single bond to a double bond, not surprisingly, it goes up in energy. It's a stronger bond. It's going to have a higher frequency. And as you go from a double bond to a triple bond here in carbon monoxide, the carbon monoxide IR, very IR active, we can observe carbon monoxide stretching at 2,143 wave numbers. But we don't need to be that specific or that exacting with where that, but we want to develop a sense for the kind of the areas. So in the 3,000 to 4,000 wave number area, these are all going to be bonds to hydrogen, because again, that light atom of the hydrogen is really going to dominate the observed stretching frequency. So whether it's oxygen-hydrogen bond, a nitrogen-hydrogen bond, or a carbon-hydrogen bond, we're going to see those in the kind of 3,000 to 4,000 region. Triple bonds are a unique signature in IR. They're kind of in no man's land where nothing else is, between 2,000 and 3,000 wave numbers. Both carbon-carbon triple bonds and carbon-nitrogen triple bonds will fall in the region between 2,000 and 3,000 wave numbers. Double bonds, we're going to see a lot of double bonds in IR spectroscopy, especially carbon-oxygen double bonds, but also carbon-carbon double bonds and carbon-nitrogen double bonds between the 1,500 and 2,000 wave number region. And finally, and probably least helpful to us really, single bonds. We're going to see lots of single bonds, obviously single bonds to atoms other than hydrogen. For instance, carbon-oxygen, carbon-fluorine, carbon-chlorine, carbon-bromine. You just go down the list, right? All this kind of 500 to 1,500, but lots of stuff goes on down there. We often call it the fingerprint region. And so let's take a look at why this is, right? In the HX region, the carbon-hydrogen, nitrogen-hydrogen, oxygen-hydrogen, notice that the reduced mass of those are all essentially identical, right? So it's not the reduced mass in that Hooke's law formula that's going to dictate the observed stretching frequency. Rather, it's going to be the bond strength. And a carbon-hydrogen bond is the weakest of those at 104 kcals per mole. And as you get a more electronegative atom bound to hydrogen, that bond length shortens, that bond length strengthens, and the observed stretching frequency goes up in energy. So a carbon-hydrogen bond, right around 3,000 is the number you want to remember. A nitrogen-hydrogen bond, now 3,300 or greater. And for an oxygen-hydrogen bond, we calculate it to be like 3,500 to 3,600 wave numbers. So the reduced masses are the same, are essentially identical, but the bond strength really dominates what's gone. However, it is important to note, asterisk, star, call out, shout out, whatever you need to do, these are calculated numbers for hydrogen atoms that are not undergoing any hydrogen bonding, which for nitrogen, hydrogen, and oxygen hydrogen bonds is pretty rare. And so what we are going to observe is actually going to be a little bit different than those numbers that we calculate. So let's take it. Let's look at some carbon-hydrogen bonds first, the one that can't hydrogen bond, and look at the trend as we move from sp hybridized to sp3 hybridized. These are all end up making for very good ranking questions, right? Essentially asking about the bond strength, but I can ask it in terms of what is the observed carbon-hydrogen stretching frequency, or rank the observed carbon-hydrogen stretching frequency and be even better. So an sp hybridized carbon to a hybrogen, bond strength 131, we're going to observe a stretching frequency really quite high, around 3,300 wave number. Whereas you move to an sp2 hybridized carbon-hydrogen bond, bond strength drops significantly. We see that just above 3,000 wave numbers. And then for the sp3 hybridized carbon-hydrogen bond, the weakest carbon-hydrogen bond, it's also going to be the lowest energy stretching frequency, and we see values that end up being just below 3,000 wave numbers. So here's an example, an actual spectrum of phenylacetylene here, an IR spectrum, and we see that down here we've got the carbon-hydrogen stretch right at 3,300 wave numbers, as we'd expect. And in conjunction with that, we see the carbon-carbon that peak at right around 2,100 wave numbers, indicating, right, that's in that triple bond region. And so the combination of those two bits of information together confirm for us that yes, indeed, we have an acetylene, a terminal carbon-hydrogen bond. That's important for us to do because that acetylene carbon-hydrogen bond falls right in the same region as the nitrogen-hydrogen bond. Similar reduced mass, and now similar bond strength, and so they fall in the same area. So using only this area right here, right? If you're only looking at kind of the CH region, you couldn't definitively say that you've got an alkyne or that you've got an amine. You've got to take other things into account. But seeing this here in red with the carbon-carbon triple bond area in blue really kind of gives you some additional evidence that we've got an alkyne. Here is going to be one of the most important and most widely used bits from IR spectroscopy for the rest of this semester and into next semester. And it's this dividing line right at 3,000 wave numbers. So for an sp3 hybridized carbon-hydrogen stretch, those signals right in some very sharp and precise cutoff, just we got lucky and it falls in a nice even number. Anything below 3,000 wave numbers, we know we are going to have an sp3 carbon-hydrogen stretch. And then anything just above, just higher in energy than 3,000 wave numbers, we know it's going to be a carbon-hydrogen stretch for a hydrogen that's bound to an sp2 hybridized carbon. And so it's a very important line for us. If you think you might have an alkene or a benzene ring, you want to look to this area and confirm that yes, indeed, you've got a sp2 hybridized carbon bound to a hydrogen. That'll be an important bit of evidence for us. And notice on here, right, there's lots of other stuff going on, but for our purposes, right, we're really going to kind of use this area in around 3000 is a very important way to gather information as we deduce what structures are using IR spectroscopy. All right, let's look at a couple of other examples. Now we're going to look at the nitrogen-hydrogen bond. So here's an aniline. We've got a nitrogen-hydrogen. We got an area here where we've got our CH stretching, right? Because we've got those, we've got kind of peaks both below and above 3000. That makes sense. We've got the methyl group on the nitrogen. So we're going to have some CH stretching on the methyl group that we observe that's kind of below 3000. But then, of course, we've got all of the hydrogens around the benzene ring that are all attached to those sp2 hybridized carbons, and we see them there. But then off to the left there, that's the important peak. And it's just a single peak. We've got an NH stretch there, the 1H. And so we see that in the IR. If we look at an unsubstituted aniline right next door, we see something a little bit different, a slight variation on what we saw. The CH bond region looks similar, except for now notice we don't have any, right, that 3000 line of demarcation, we don't have anything lower in energy in that because we no longer have any sp3 hybridized carbon hydrogen stretches. That's not the only thing that's different. What else is different is the region highlighted in red there. The reason we have not one peak but two different peaks, right? Two different peaks tells us that we are going to invoke some stretching mode at two different frequencies, right? It's if those of you that have had a musical background, right? There are two different resonant frequencies, right? This aniline is sympathetic with two different energies that will invoke some stretching, and we see that here in this kind of anti-symmetric NH2 stretch and a symmetric NH2 stretch. So it's right, either in the anti-symmetric, one nitrogen-hydrogen bond is getting longer while the other gets shorter, and vice versa, and it kind of goes back and forth. Or in the symmetric stretch, they're both getting longer at the same time and then both getting shorter at the same time. Both getting longer at the same time, both getting shorter at the same time. But they're both IR active stretches, so we see them, and they occur at different energies. So I always remember those as kind of like Dracula fangs, right? The vampire fangs there. Those two vampire fangs are going to be telling us that we've got kind of this symmetric anti-symmetric stretch going on, and it really points to a primary amine, an NH2, because you've got to have that primary amine to observe that. All right, so I said that all of these oxygen, hydrogen, and nitrogen, hydrogen stretching frequencies were calculated, but with a caveat that it didn't include the impacts of hydrogen bonding. Now, hydrogen bonding, you might wonder why I have a picture of my wife and my dog with their tongues out. Well, hydrogen bonding, the impact of that is we get this region on the IR spectra that looks a lot like a dog's tongue. This kind of wide, loopy, broad region, which is saying that we can activate some stretching frequency across a very wide range of energy, right? So our oxygen-hydrogen begins to stretch, right? It's sympathetic to a wide range of energies there, and the result manifests itself in this loopy dog's tongue looking signal. And if we look at, again, if we use just Hooke's law and plug in the numbers, we know the strength of an oxygen-hydrogen bond. We can plug in that number. We know the atomic mass of oxygen. We know the atomic mass of hydrogen. We plug all those numbers into our Hooke's law formula, and we come up with a number that is 3,550, right where this pink bar is. And yet that's not what we see when we do when we take the IR of phenol. So let's take a look at why this is, right? This big loopy dog's tongue. We know If we got alcohols around, there's not just a single atom of phenol. There are going to be a number of phenol residues around, and there's a dipole moment. We can have hydrogen bonding from one alcohol to the next alcohol. That active hydrogen bond, right, weakens and lengthens the hydrogen bond, or the oxygen-hydrogen covalent bond, and that's why we have in a solution or in a beaker of phenol, we have a range of different lengths and strengths of oxygen-hydrogen bonds around due to this hydrogen bonding effect. And so we see that it's sympathetic with a stretching, or which shows sympathetic stretching vibrational frequencies across a wide range. Carboxylic acids are also very diagnostic, right? When we see this in the IR, we no longer have that nice loopy dog's tongue because carboxylic acids will have a tendency to hydrogen bond in pairs, right? They'll make a dimer together and form a very well-defined thing, and you have this broad kind of OH stretching regions for the carboxylic acid. It's very broad, kind of a weaker stretch, and we see this area here kind of on the side. On the side we call shouldering. So let's look at an example of an alcohol. Here, instead of phenol now, we've picked BHT. BHT stands for butylated hydroxytoluene. BHT you probably eat on a daily basis. Butylated hydroxytoluene is a very common antioxidant chucked in, a food preservative chucked into things to slow down the decomposition and oxidation. So even though you don't know, you've had lots of exposure to BHT. BHT, because of those large tert butyl groups on either side of the oxygen, those large tert butyl groups act as a shroud or act to block the ability for BHT to hydrogen bond with its neighbor. So this big steric bulk makes it so it can't hydrogen bond. Whoops. And we see, yes indeed, remember where we had that pink bar before, exactly as Hooke's law calculates for us, that's where we see the observed oxygen-hydrogen bond. We don't see this big, loopy, dog's tongue looking thing because we can't hydrogen bond in BHT. All right, a couple of other important regions for us, especially double bonds, carbon-carbon double bonds. It's going to be helpful for us to check and look in the IR right around 1640. Unfortunately, it's kind of got a weak absorption, and so it's sometimes difficult to really see clearly. Carbon-carbon double bonds, you'll usually look to things like proton or carbon NMR to really confirm your suspicions if you think you have a carbon-carbon double bond in IR. However, carbon-oxygen double bonds, IR is going to be kind of your go-to diagnostic tool. It's a very strong absorption. It's very, very indicative, right? So a little bit above 1500. Some things can get as low as that. Really, the number I always remember is 1700, and then 1700 plus or minus a little bit based on the flavor of carbonyl. But it's a very strong, very obvious stretching frequency. And then nitro, also we have the two bands again, and the two bands, because the nitrogen is bound to not one but two oxygens, we're going to have the symmetric and antisymmetric stretches. And so the strength of the IR depends on the dipole moment. We see a very strong dipole of a nitro group. It's a very, very strong absorption in the IR, although nitro groups are a little less common than carbonyls for us. All right, that does it for the background and theory for IR. Now it's time for a little bit more theory. That's why our poor polar bear is like, I want to stop doing physics now. But we're going to talk just a little bit of theory about NMR. And maybe you've seen this before, maybe not, but it's nice to help us understand at least a little bit what is going on in the NMR. So when you put a sample in your NMR, right, that big NMR thing, it's a huge magnet. So we put it in the center of this big magnet in this big magnetic field, and we're going to have a tendency to align all of our nuclei within that magnetic field. And once we kind of all get them in this, put them in the magnetic field, they're all going to have this relative similar alignment. And then what we are going to do is we are going to pump in a radio wave that turns out right where these nuclei are have some resonance. And so if we pulse in a radio wave, we are going to be able to take those nuclei, and what is going to happen is we are going to move them up in energy. You just want to think of it as, for now, it's absorbed some energy. It is now at a higher energy state. But it's not going to stay in that higher energy state. Eventually, it's going to drop back down to the ground state energetically. And when it drops back down to that ground state energetically, again, it has to give off that same amount of energy that it absorbed in the first place, and that is what we detect in the NMR. And so some considerations to think about for an NMR: not all protons are created equal. So the amount of energy that it takes to excite a proton that's bound to an sp2 hybridized carbon is going to be slightly different than the amount of energy it takes to excite a proton, the nucleus of a proton, right, that is bound to an sp3 hybridized carbon. And neighboring oxygens or fluorines or aromatic rings are all going to have an impact, and all of these different protons on our molecule are going to be excited at a slightly different radio wave frequency. And so what the NMR does will scan across a range. Well, they used to scan across a range. Now they just shoot the whole range in all at once, right? They look across an entire range of energy so that they can detect all of these different types of protons. And then again, all those protons will relax down, shoot that energy quanta back to a detector. The detector says, hey, this is a certain energy. And we look at the spectrum and say, oh, well, that must be an sp3 hybridized carbon that is next to a carbonyl carbon. So here's an example of what a spectrum would look like on a given molecule. Here we go. We've got a lot of different types of protons in here, HA through HG. We look at those, all different range of things, and they all have different signals. And we're going to talk a little bit more about the signals and what they mean and who they belong to. And we'll look at assigning those in a little bit, but we're not too concerned about that right now. There is an electrostatic potential map of that same alpha-beta unsaturated ketone, and we can actually see that, right, electronically each of these are a little bit different. We can appreciate it pictorially, but it's nice and clear in the NMR. So why do we want to use NMR, right? We want to use NMR to look at a spectrum and say, yes, this is the product that I thought I planned on going and making a lab, or right, so we're kind of armed already with some information because we have some expectation. Or the more difficult one is to actually elucidate a completely unknown structure. Like somebody hands you a vial and says, tell me what this is. You're starting at square one to elucidate an unknown structure from spectra. So we're going to go over this. We're going to solve some problems in lab during class. And I really take the approach of keep it as simple as humanly possible. The more complex, the more mired down you get in minutia, the more likely you are to make mistakes. So don't get mired down in minutia and just look at the most obvious, most helpful, most diagnostic things in the spectra. So one of those is, right, the number of signals, right? Each set of chemically equivalent protons will give rise to a chemical shift, right? It'll give you a signal. So a CH2 group, or both of those hydrogens are chemically equivalent, will give you a single signal. A different CH2 group somewhere else on the molecule will give rise to a second, different, unique chemical shift. Now, the degree of uniqueness, there might be occasions where signals begin to overlap because they're not so unique. They are very similar, and they come similar places in the energy spectrum. but they should each give their own unique chemical shift. The next most important thing is to figure out for each of those signals, right, the area under the peak is proportional to the number of hydrogens. So if you've got one peak and the area under the peak, you come up with some number 12, and you look at another peak and the area under that peak is 24, then the ratio of those two is 2 to 1. Right? This will tell us the relative abundance of each of the different hydrogens. And so we see a lot of kind of 3 to 1, 2 to 1, and 3 to 2 type ratios, because those are some of the most common, right, for carbon, right, the number of hydrogens to carbon, 1, 2, or 3. Obviously, if there's 0, they don't show up in the proton NMR. So this is a very helpful tool to help us decide, is it a CH3? Is it a CH2? Is it a CH? Are there two CH3s that are identical? Things of that nature. And finally, right, and this is really kind of order of importance, if you haven't yet acquired enough information to solve the problem, now is when you'll want to look to the position of the NMR signals, right? The chemical shifts, how far downfield they are. The area in which they exist will kind of give you some indication of where they might be bound or what types of motifs they might be bound to. That is the functional group where they are near. All right, so here are two examples. We've got an alcohol on the left and we've got an ether on the right. So we got neopentyl alcohol on the left and methyl tert-butyl ether, MTBE. It used to be a fuel additive until we found out it kind of sticks around in our water system. It used to be a fuel additive, an ether on the right. Well, which spectra goes with which? So we've got all singlets, there's no splitting, chemical shift, but it's easy to look at and tell because on this spectrum on the left here, we only have 2 signals, and on the spectrum on the right here, we have 3 signals. So the question is, well, how many unique protons would we expect? And if we look at the alcohol here on the left, well, each of these 3 CH3 groups are going to be chemically equivalent. And then the CH2 group is going to be a unique signal, giving us 2. But don't forget about the OH, right? That hydrogen will also show up. We should have 3 signals in the NMR. Conversely, if we look at the ether, CH3, again, all 3 of these should be the same. No hydrogen there. And then this CH3 down here should also be the same. I think that's what we've got. 3 signals there, 2 signals here, 3 signals there, 2 signals here, and that's the winner. So it's sometimes solving the problem can be as easy as that. Start with the kind of easiest, most straightforward explanation, rationalization, and only get more complicated and more complex if you need to. Yes, there we go. All right. But yes, indeed, the relative chemical shifts can be helpful on occasion. Now, you're not going to be required to memorize chemical shifts. Chemical shifts, a table of chemical shifts will always be attached to the exam, either on exam 3 or the final exam and into next semester. But the better you get with it, the less you have to rely on the chemical shift tables. And let's take a look at an example and we can spot some trends. So a boring old methyl group right around 1 part per million, a methylene, CH2, a little bit higher in energy, a methine, that is a CH, even a little bit higher in energy yet, and then something that is allylic to a pi bond, right, a little bit higher yet. Those are for saturated. We see a bigger chemical shift dynamic when we start putting different substituents on there. So let's take a look at an example across the trend from fluorine to oxygen to nitrogen. Right? Fluorine is most electronegative. That hydrogen would be kind of in the 4.5 plus or minus a little bit area. Whereas the hydrogen that is bound to a carbon that is also bound to an oxygen a little less electronegative. It's not going to be quite as deshielded. It's going to be closer to the 3.5 plus or minus a little bit. And then the trend continues for nitrogen. Nitrogen is going to be 2.5 plus or minus a little bit. we can see an additive effect, right? So two oxygens bound to the same carbon, the hydrogen that is bound to that carbon now way up at 5.5, where chlorine is going to be a little less electronegative than fluorine, and bromine even less electronegative yet. So again, the general trend is electron withdrawing groups reduce electron density at neighboring hydrogens and decreases the ability of nearby electrons to shield the nucleus, causing chemical shifts to appear downfield. Right? So this notion that electron withdrawing groups pull the electron cloud, like de-shroud the nucleus, making that nucleus kind of more susceptible to interrogation, moves it downfield at higher energy in the NMR region. We can do the same thing for unsaturated groups. So a terminal alkyne, 2.5, and the carbon-carbon double bond, an sp2 hybridized carbon, actually higher in energy. This is an interesting notion, and actually you should ask me about it on Monday, and I'll draw a little picture on the board, because this doesn't quite fit with our expected trend, right? We saw the alkyl groups kind of low energy, about 1.5. We'd expect the trend to go from sp3 into sp2 and follow the sp, but that is not the trend. The sp is actually snuck in between the sp3 and the sp2 energetically. Similarly with benzene, or an alkene that's got an electron withdrawing group, so it looks like a good dienophile up there, and especially an aldehyde. These are all very indicative regions. For us, right, the area around, practically the area around between 7 and 8 is going to be important, because it's going to help us think or recognize that we probably have a benzene or a related type compound. Similarly, it doesn't pop up very often, but then it's 9 to 10 region. When you've got an aldehyde, this hydrogen, very diagnostic, exists up here, very deshielded, very far downfield. And then lastly, coupling, right? We call this a multiplicity, right? This notion of singlets, doublets, triplets, quartets, etc. So if we have this signal that we're looking at the signal HA in all these cases, and we'll assume that if I haven't explicitly put an HB on there, that it's just some other alkyl group. It's a non-proton. And so HA there with no adjacent carbon-hydrogen bonds, there's no coupling. We will just see a singlet. But in the event that HA has one nearest neighbor, HB, we are going to see HA split into a doublet. And correspondingly, we will see that HB is also split into a doublet by HA. If we continue to look at HA and go to now have two hydrogen nearest neighbors that are identical, importantly, they are identical, both are HB, chemically equivalent, we should fit into a triplet. And then one more, this HA that's next to three adjacent chemically equivalent protons should give us a quartet and this nice 1 to 3 to 3 to 1 ratio. So predicting multiplicity, right? Number of peak in a multiplet follows the so-called n+1 rule, where n is the number of adjacent protons. We just saw if there's 2 protons, it's split into a triplet. If there are 3 protons, it's split into a quartet. If there are 4 protons, it's split into a quintet. All right, so a little bit of practice now, so you can pause the video, take a look and give an idea. Practice now and get a drink of coffee and unpause when you're done. Okay, we are back. Let's take a look. Yes, should be a singlet, should be a triplet, and should be a quartet for those 3 signals. On the right molecule, again, a singlet, now a septet, and a doublet. So that septet signal, it is a single hydrogen that has 6 equivalent hydrogen nearest neighbors, n+1, 6 + 1 = 7. We call that a septet. And not all coupling is quite equal. We're not going to get into the hows and whys and whats of coupling, but coupling can be diagnostic, although it is kind of the lowest of the low in terms of importance of really elucidating a structure. Sometimes it will help corroborate things, but in general, they are just going to be a little bit of corroborating evidence and not particularly useful for us to actually solve from scratch an unknown molecule. If you're getting into the J values, probably you've long ago solved the actual structure and you're just looking for some reinforcement. So just a regular run-of-the-mill sp3 coupling in the neighborhood of 6 to 8 hertz. Around a cyclohexane ring, it's a little bit different because we've got this kind of cis and trans type of thing. So when we have a 180-degree dihedral, as we see there, HA-HB, we can get a very large coupling constant up to 12, 13, 14 hertz. However, when they are cis, a 60-degree dihedral angle, we see a much smaller coupling constant, as low as essentially invisible, no coupling, up to about 5 hertz. Similarly, 0 to 5 hertz in a different 60-degree dihedral, again because it's all 60-degree dihedrals. Here in a transalkene, this is kind of one of the biggest. It's similar to that trans cyclohexane, a very large coupling constant indicates a trans orientation, 180-degree dihedral. So notice right above it, 180-degree dihedral between HA and HB, similar across the transalkene, 180-degree dihedral angle, same large coupling constant. As we go to 0-degree dihedral angle, HA and HB, a little bit smaller. And we can even see, notice on this next one, some geminal coupling. So this is not a nearest neighbor, right, because the adjacent carbon to HA is here. But on occasion, if HA and HB are different, that is if we have two different alkyl groups over here and making HA and HB different, they can couple to one another. Again, we don't see this hardly ever, not particular diagnostic. Neither is this next thing here, where, right, on occasion you can see some coupling, but it is so rare that I've just put 0 hertz. You skip one carbon, and suddenly the next carbon over and its bonds to hydrogen, it's too far removed. We lost the lines of communication from HA to HB. They don't couple. You don't see any observed coupling in the NMR. So yeah, we saw coupling on adjacent protons, which is by far the most common vicinal coupling. On the same carbon, again, geminal coupling, but we don't see it all that much except for on the case of the alkene. So let's look at an example, jump right in, and we can see just how powerful the kind of top-down approach is. Because here is a NMR spectrum. It's got lots of information there. We've got integrations, we've got splitting, quartets, triplets, we've got 4 different signals. But let's start with the most important thing, the number of signals. We have 4 unique signals in this NMR, and so if we're given a choice like this, let's eliminate some of the low-hanging fruit that's easy to see it's not that. So any of the compounds up here that don't have 4 signals, we can eliminate right off the bat. So I look at A and I see a methyl, a CH2, and then an OH. Okay, I think that one would probably have 4. But I look at B then, and I see that it's got only 2 equivalent methyl groups and 2 equivalent hydroxyl groups. I would only expect to see 2 signals for B, so B is out. Let's look at C. C again, I've got a CH3 to CH2, and then a CH2 and an OH. Okay, that's still legitimate. We've got 4 different signals, seems reasonable. How about D? Again, we've got 2 methyl groups, those are going to be the same. We've got the hydrogen that's on the alcohol, and then we've got one more hydrogen right here connected to this ether-like linkage, or actually peroxy linkage. But we've only got 1, 2, 3. D is out because we've only got 3 signals. And then similar E, this methyl group and this methyl group are the same. This methylene would be a second different signal, but again, only 2 signals. So we've already made our problem 60% easier by eliminating the 3 least reasonable choices just based on the number. All right, and then the world is your oyster. You can use integrations, might be helpful. But integrations, look, we got a 2H, a 2H, a 3H, and a 1H. I think both of these kind of work for that. This one's got the two 2H's, a 3H and a 1H. Here we've got a 3H, we got a 2H, a 2H, and a 1H. That doesn't help. But we should fairly quickly recognize that here we should have CH3, a CH2, and a CH2, and then a nice singlet. So all of these will undergo vicinal coupling and be split into whatever they're split into, triplets, quartets, quintets, etc. However, over on C, this carbon-hydrogen bond here is what we call isolated. We're not going to see any coupling. So we should have a singlet here, we should have a singlet for this, and we should have, well, this is next to a CH3, it should be a quartet, and this is next to a CH2, so we should have a triplet. That is in fact what we see. But even without getting into the nitty-gritty, we just looked on the left and said, well, A is not going to have two singlets, so it can't be A. C is the answer. So only use as much information as you need to come to your conclusion, and then certainly double back and look for corroboration for your result. But the more complex you make it on yourself, the more opportunity you give for misassigning these compounds. All right, so carbon NMR. We've seen carbon NMR a little bit. A lot of the same fundamentals as proton NMR. In general, proximity to electron withdrawing groups leads to a downfield shift, right, to the left. But again, the most important bit of information you get from a carbon NMR is the number of unique signals. For the compound on the left, 1, 2, 3, 4, 5, 6, we have 6 unique carbons. We see that we have 6 unique carbons down here. The compound on the right, all 3 of these carbons that are methyl groups are chemically equivalent. So that's 1. Then we've got this carbon, 2, 3, and 4. We only see 4 carbons. So right away, right, that helps. But let's take a look at a couple of these, right there, general chemical shifts. A, B, C, and D makes sense. C is that carbonyl carbon. B is the carbon right next to the oxygen, and D is the carbon next to the carbonyl. So we see that makes sense. Similar A through F over there. But again, that's only of kind of secondary importance from the carbon NMR. The most important bit of information we get from the carbon NMR is simply the overall number of signals. And again, this information will be given to you. You'll always have a list of kind of chemical shift regions where you'd see different functional groups in a carbon NMR, but it's nice to develop a feel for it and kind of, avoid digging into these long, dense, elaborate tables. But the regions that are going to be important for us, right, for 150 up to 200, really, we're thinking carbonyl. Now, this is not an inclusive region. Carbonyls can exist all the way down to 130 even, or all the way up to 240 or 250 or 260. So there is certainly overlap. They are not clear lines of demarcation, but the general area in purple, you're kind of thinking it might be a carbonyl around. Similarly, this area in red really points to carbon-carbon double bonds, right? Carbons that are part of either alkenes or benzene rings, aromatic molecules. In the area in green, these are bonds, areas to electronegative atoms. Carbon-oxygen bonds, carbon-chlorine bonds, carbon-fluorine bonds, carbon-nitrogen bonds, right? Just go right down the list. You'd expect to see them there. And you could use your understanding of electronegativity to kind of guess relative trends across that region in green based on how electronegative the atom is. The more electronegative, the further to the left it will be. Area in yellow, here's now, it's really starting to get a little bit more murky down here, but in the area of kind of 30 to 50, it's not connected to an electron withdrawing group, but maybe it's connected to the carbon is next to the carbon that has an electron withdrawing group as part of it. And then the boring region in here in blue, just kind of your regular run-of-the-mill sp3 hybridized carbons. We'll see a lot of stuff down there, right? CH3s, CH2s, CHs, cyclohexane rings, things like that, all going to be in that boring alkane region. Similarly with carbon NMR, we can use these same tools before you even jump into chemical shift and say, oh, what does it mean if I got a signal at 160? Or what are those two? Why are they two so close together at 130 or 90? Or what's it mean at 50? Or I don't have anything at 10. Calm down there. You can often use a very straightforward top-down simple approach to really limit the number of possibilities. For example, if we want to identify which of these compounds leads to a carbon NMR signal might look like this. I look at A and I say, well, A, because we've got symmetry here, we've got symmetry here, this carbon and this carbon, those two carbon, oops, oh geez. I guess you know it's not going to be that one. This carbon and this carbon are the same, these carbons are the same. I'd only expect to see two signals for compound A, it can't be compound A. For compound B, I would expect to see 1, 2, those two are the same, 3, those two are the same, and 4 signals. Again, not going to be this because we're looking for a compound with 7 signals. For C, I would expect these two to be the same, these two to be the same, and those two to be the same. So 1, 2, 3 around the ring. And then again, by symmetry, both of these methyl groups are the same. So 1, 2, 3, 4 unique carbons. Can't be this one. For D, here we go, around the ring, 1, 2, 3, 4, 5, 6, all of these, because we no longer have any symmetry, we no longer have kind of any mirror planes that were one side or the other is the same. We've got 6 unique carbons all the way around that ring, and then the methyl group leads to the 7th possibility. That is what we see down here, but let's look at E for one more possibility. Again, E around that benzene ring, we've got 6 different carbons, but out here the carbonyl is a 7th one, and that methyl group is an 8th one, and the tert-butyl group is going to give you 2 more, and I expect 10 carbons there. D is the winner without even looking at chemical shift. And the reason I picked this one is because notice we've got a signal here in the 160 parts per million. And if we go back, right, that 106, if you went right to the chemical shift table and said, oh, 160 is right in the carbonyl region, 160 right in the carbonyl region, only one of these compounds has a carbonyl, and that's this ketone E. You pick E, you don't even think of the other things, and then you get the wrong answer. But again, these chemical shift regions are actually much broader. And the reason that this chemical shift right here at 160, it is from this carbon right here that is sp2 hybridized in the benzene ring. On top of that, it is also attached to this electronegative oxygen. So it is an additive effect that is both part of an aromatic ring and it is bound to electronegative atom. The combination of those two moves it out of our kind of standard aromatic region and up to this area where if you started there, and said, I must have a carbonyl, only one of these compounds has a carbonyl, you'd get the wrong answer. Oh yeah. And last thing for the day, calculating degrees of unsaturation. Very diagnostic, very helpful, gives you an idea of like how to come up with these things. So to calculate the unsaturation from a formula, it's the number of the carbon atoms minus half of the number of hydrogen and halogen atoms. So you count hydrogens, chlorines, fluorines, bromines the same. And then if in the event you have a nitrogen, you have to add half of the number of hydrogen atoms. And at the very end, after all that, you get to add one more, just because we like to add one in spectroscopy. But you get to ignore oxygen, right? So for example, this top molecule, we can see that there are there's 1 degree of unsaturation here, this pi bond, right? And we can see, right, again, the number of carbons, 4, minus half of the number of hydrogens, 8 divided by 2 is 4, so 4 minus 4 is 0, but then, again, the plus 1 at the end, 1 degree of unsaturation. For benzene, 1, 2, 3 degrees of unsaturation, the 3 pi bonds, but then a 4th degree of unsaturation for a ring. So both pi bonds and rings, any pi bond, any ring, is a degree of unsaturation. And we can double check that we get 4 with C6H6. 6 minus half of 6 is 3. 6 minus 3 is 3. Plus 1 is 4. Yes, 4 degrees of unsaturation. Similar, 7 minus half of 10 is 5. 7 minus 5 is 2 plus 1, because we get to ignore oxygen. 7 minus 5, 2 plus 1 is 3. We get a pi bond. We get a pi bond, and we get a ring for 3 degrees of unsaturation. So you get the idea there. All right, we are done for the flip videos. This is right where we're going to pick up on Monday and look at solving some of our first problems. And we'll start straightforward and get more complex. But that is it for us this week. Enjoy the video and enjoy the rest of your weekend.